Hello everyone, welcome to COMP359, Design and Analysis of Algorithms. In this video, we are going to continue our discussion about solving recurrence relations. And here we are going to focus on another method to solve the relations, which is called master method or master theorem. In the previous video, we have seen two different methods to solve recurrence relations like this, t of n equal to 2, t of n divided by 2 plus 1, using the substitution method or using the recursion tree. Here you can actually see the recursion tree for this relation. This example, we have actually seen it in the previous video. I just actually thought it's going to be a good review to start the video. So you can see this tree is going to, in fact, just show that, for example, t of n, each t of n is going to be 2t of n divided by 2 plus some actually additional cost 1, right? So in the tree, we just actually will see all the terms of t of n. And this tree, at each level, it will actually grow. And for example, this all of these nodes, t of n divided by 2, each one using the same relation, I can actually say that t of n divided by 2 will be 2t of n divided by 4. And it will actually grow until we reach to t of 1, which we know that the cost of t of 1 will be constant, and we can actually stop growing the tree at this level. After creating the recursion tree, we need to add all the costs for each of these boxes or each of these nodes in the tree. In this example, the additional cost that we have is going to be a constant cost that we just show it using 1. So for each of the boxes, some costs or that additional time will be added, and at the end, the total cost or the total result of t of n will be the summation of all of these associated costs over all of the nodes in our recursion tree. To make it simpler, we actually said that if you calculate the summation of these costs level by level and then add up all of them, it's going to be easier. So in the first level, the only cost that we have is going to be 1. In the second level, you are going to have 2 boxes. For each one, you are going to have the cost 1. So it's going to be, here the cost is 1, here the cost is going to be 2, here the cost is going to be 4 actually boxes you have. So here the cost is going to be 4, or we can actually write it as 2 power 2. In the next level, the cost would be 2 power 3, because all of these boxes will be actually going to 2 other boxes. And these costs are going down until at the last level, or the depth k of the tree, you are going to have 2 power k number of boxes. For each one, the cost is 1. So in total, the cost is going to be this summation, the summation from, you can actually write it as 2 to the power of I. This is going to be a geometric, summation, and the upper bound is k. What is k? K is, in fact, just tells you that when you reach to the, the leaf level, where n divided by 2 to the power k is equal to 1, where k will be equal to log of n, right? So this summation will be 2 to the power of k plus 1, or you can write it as 2 multiplied by 2 to the power of k. 2 to the power of k is equal to n. So in total, the cost will be 2n, or you can write it as theta of n. So t of n will be equal to theta of n or O of n. So you say that this, after solving this recurrence relation, the result of t of n will be in big O of n or theta of n. Okay, so this method that we have applied over the this recurrence relation, we can generalize it and write the master theorem. So the general form that I have written here is this recurrence relation, that T of n equal to A multiplied by T of n divided by B plus some additional cost, which is in the form of n to the power of d. Okay, I'm going to show the master theorem using this general form and show you that in fact we can get out 3 simple formulas for 3 different cases, and the total is going to be called the master theorem. What that has been actually discussed in your textbook is slightly different than the version that I'm discussing here. In that version, instead of this function n to the power d, in your textbook CLRS, it has been written as f of n. So this format, I mean the one that has been discussed in your textbook, is a little bit more general than this form, but kind of harder to prove. So I thought to simplify to this format that the f of n that you have is going to be n to the power of d. So we will see that proving this is going to be much easier, and you will be able to use this proof to solve even some other actually cases that are not directly fit in master theorem, in the form of the master theorem. So this version is going to be much easier for you to understand and later on to use it in practice. Okay, so let's just actually get back to this general form that I have here. Let's just clean up a little bit. There are some constraints about, you can see that there are some constraints over the coefficients that I have here. First of all, A should be some positive number greater than or equal to 1. B should be some positive number greater than 1. So you can see that this is important, and when you are writing your recurrence relation, you should just think about it as a, some problem that you are solving it in a recursive format. So this sub-problem should be of a smaller size. If you make it of greater size, or B is equal to 1, so a relation like this is not solvable. So that's why B needs to be something greater than 1. And another restriction is that this function that you have here should be n to the power of something, but it doesn't matter what is going to be the value of d. So for example, the value of d even can be actually 1 over 2, any positive actually value, right? Any positive value, or it can be actually equal to 0 as well. So this format is going to cover a lot of different recurrence relations. Now let's see that how we can actually solve a general form of recurrence relations like this using recursion tree. Okay, if I have a recurrence relation like this figure that I'm actually showing to you here, each of these dots are going to be a knot in my tree, right? So the top one is in fact actually corresponding to T of n. For each of the levels, this part here, this column here, is showing the size of the problem. So at the top, the size of the problem is going to be n. At the next level, the size of the problem, the size of each of this is going to be n divided by b, right? So each of these nodes are going to be corresponding to Tn divided by b. And how many of them you have? A different branching factors, a different actually nodes. So for a different number of T of n divided by B. Okay, so you can see that this is exactly the recursion tree that we have discussed before. In the next level, each of these nodes again are going to be corresponding to T of n divided by B power 2. So you can see that it shows that the size of the problem is going to be n divided by B power 2. And of course, each of the previous nodes will going to have a number of branches. Okay, so it is showing the full tree. What is going to be the depth of the tree? The depth of the tree is going to be when you reach to the size of 1. So n divided by B power k will be equal to 1. So what is k? K is going to be the depth of the tree, how many levels you are going down. K will be equal to log of n, the log of n in base B, right? Because you can actually just simplify this one. N will be equal to B to the power of k, and if you take the log from both sides, you will reach to k will be equal to the log of n in base B. That's why it's actually just written here that the depth of the tree will be log of n in base B. Okay, so let me just clean up a little bit here. Okay, so this is going to be the full tree. We know that what is going to be the depth. We know what is going to be the size of each of the problems in each level, right? So now if we want to solve the full relation, what is going to be the answer for T of n, we need to calculate the cost for each level and then add up all of those costs. What is going to be the cost for the first level? Remember, associated to each of these T of n's, let me use a different color. Each of the nodes here, each T of n, there is going to be some additional costs, right? So T of n is equal to a number of T of n divided by 2 plus this additional cost that I have here, this term. So based on the size, what is going to be the size of the first level? The size is n, and the formula is n to the power of d. So the cost for the first level is going to be n to the power of d. What is going to be the cost for the second level? The size of the problem is n divided by b. The formula was n to the d, so the whatever is the size to the power of d. How about the next level? Again, the size is n divided by b to the power of 2. And you need to actually take all of it to the power of d. Okay, one thing that I forgot is that for each of these boxes, the cost is going to be n divided by b to the power of d. How many of them I have? I have a number of these boxes. So I need to actually multiply a to that as well. How many of these boxes are I will have a to the power of 2 number of these costs. Okay, so if I wanted to write down a more general formula for example, at the level, for example, t, it will be something like a to the power of t n. You can write it as, you can see that this power here and this power here is the same, right? I am going to take that part out. So the full formula is going to be something like this. The cost of, the total cost at level t will be something like this. A to the power of t b to the power of td divided by n to the power of d. So I need to add up all of these costs until the last level. Okay, so until the last level, which is going to be in the last level, all of the costs are going to be again, the size is 1, but the number of actually sub-problems that I have is going to be a to the power of k. So this is going to be the total cost for the last level. So you can see that I have a very nice pattern of numbers that I can write down the full summation as something like this. Okay, so you can see that what is the value of k? The value of k is the depth of the tree, right? Which is going to, we have actually discussed that, it is going to be log of n in base b. You can see that this term that I have here, all of these terms, are going to have n to the power of d that I take out from the summation, and the rest of it is going to be, a geometric summation. That the term in this geometric summation is going to be a divided by b power d, the whole ratio to the power of I, where I is changing from 0, here I is 0, and here I is going to be equal to k, where k is going to be log of n in base b. Okay, so this is a geometric summation, and it will also have this additional term n to the power of d. Right? So I can actually end up to have this full summation as the result of t of n, where r is that ratio that we have discussed about it, which is going to be a divided by b to the power of d. Okay, if you haven't actually got the, all of the levels properly, and you feel you got confused, you just get back to the recursion tree and try to, calculate the cost of each level. Okay, just write down all of it together for yourself. You can pause the video and just write it down for yourself. This is very important. If you learn this discussion and you learn that how we got the formula, you would never forget it. You don't need to memorize the formula, because you learned it. You know that how to get it, even if you actually forget about the details of the numbers. You just need to draw the tree and just calculate the cost of each level, add up all of them, and then you will actually end up to a formula like this. So this is not going to be a very complicated formula. You can just actually calculate it for any recursion tree or any recursion relation that you have. Okay, so this is going to be our final formula. Now the question is, how can I actually find the solution for different values of this ratio? This ratio, based on the formula, I can actually just calculate the ratio, but there are going to be many different cases for this ratio. I don't want you to know the exact solution for this ratio, but I wanted to give you a tip here. There is a theorem, it's a mathematical theorem. I don't want you to know all the details of it, but just memorize these three actually different cases, which is going to be the result of that. For any geometric sequence, any geometric summation that you have, based on the ratio, the result is going to be equal to This is going to be the formula. Although the formula, it looks actually complicated, but it is not. I mean, the final result is important for us. I don't want you to, memorize the full formula here. But just know that, okay, if the ratio is equal to 1, if R is equal to 1, you know that this summation is going to be very simple. All of the 1 to the power of I is always going to be equal to 1, right? So this summation is going to be equal to k plus 1 if R is equal to 1. So this is one case. If R is not equal to 1, the result will be equal to this formula. Again, I'm saying the exact formula is not really important for me, but the result of it will be important. So based on the value of R, if it is greater than if it is greater than 1, or it is less than 1, they are going to be giving me two different cases. If R, let me actually just summarize it here. If R is greater than 1, you can see that I can actually simplify this formula. This is the larger term here, and you have actually an R here. So you can say that if R is greater than 1, this formula can be written in terms of theta of R to the power of k, right? You have a term R and a term R to the power of k plus 1 in the numerator. So the result is going to be theta of R to the power of k. This is important for me, not the exact formula. So if the ratio is greater than 1, the result of this summation is going to be in theta of R to the power of k. So what would happen if the value of R is less than 1? Just make sure that you know the ratio should be something positive. It can be greater than 1, it can be less than 1, it can be equal to 1. If the ratio is less than 1 in this case, so if you go back to this formula again, if you think about it, if the ratio is less than 1, so by increasing the power, this value is actually, approaching to 0. And this one is actually going to, on the top, this part R to the power of k plus 1, when k is increasing, this term is actually approaching to 0, right? So you can actually end up removing this section, and whatever will remain is going to be a fixed value here. So that's why I'm saying that the result of this summation is going to be a fixed value. So that's why we write it as theta of 1. This is not going to be something growing. It is going to be some fixed value. So the result of this summation is going to be a constant value in case R is less than 1. This is going to be equal to R to the power of k in case R is greater than 1. And if R is equal to 1, if the ratio is equal to 1, this one is the simplest case. This is going to be equal to k plus 1, so it's going to be theta of k. So these are the three different cases that you need to always memorize. After you get this summation based on the value of the ratio, I'm going to have three cases. Either the ratio is less than 1, equal to 1, or greater than 1. So based on these three values, I can write down the full master theorem, which is telling you that if you have a recursive relation, a recurrence relation like this, based on the value of the ratio, what was the ratio? Just go back to this formula. The ratio was A divided by B to the power of D, okay? Which we actually got it exactly from the recursion tree. Okay, so based on the value of the ratio, I have three cases. If the ratio A divided by B to the power of D is equal to 1, if the ratio is 1, the result of T of N is going to be, if you go back to this formula, I'm going to actually just, exactly write it down for you. The result of this summation is going to be, if the ratio is 1, the result is going to be, theta of K, right? What was K? K was log of N in base B. And you also have this term N to the D. So you need to multiply N to the power D multiplied by log of N to the base B. So the result is going to be N to the power D log of N. You know that the bases are not important for us, so I'm going to actually just ignore that. So T of N is going to be equal to theta of this, or you can just write it as big O, N to the power T log of N. Okay, so what are the cases of, some examples like this? For example, this will actually fall in this category, in this case of the master theorem. You can see that here A is equal to 2, B is equal to 2, D is equal to 1. If you calculate the ratio was A divided by B to the power of D. This is going to be equal to 1. So if you have a relation like this, you can immediately say that, okay, this is going to be O of N log N. Okay, another case. This is very similar to that. You have A, you have B, and the D, the power of N here is going to be 1. Again, the ratio is going to be 1. The result of this recurrence relation is going to be O of N log N. How about this one? Here again, A is 4, B is 2, the value of D is 2, the ratio is going to be equal to 1. So what is going to be the time complexity? It's going to be N power 2 log N. Okay, be careful, this is going to be N to the power of D multiplied by log of N. So N to the power 2 log of N. How about this relation? It looks more complicated, but it's not. So what is the value of A in this relation? A is equal to 1, B is equal to 199, right? So you have it N divided by B. So if you have this value here, so the value of B is 100 divided by 9. And still this is correct, the value of B is greater than 1, right? The value of D is 0. So the ratio A divided by B to the power of D will be equal to 1. Whatever, because the value of D is 0, B to the power of D will be 1. Okay, so the ratio will be equal to 1. What is going to be the final lambda notation for this one is going to be log of N. Why? Because that term N to the power of D will be N to the power of 0. So this is going to be 1, and so you ignore it. So the time complexity of the last relation will be O of log of N. All of these 4 cases are going to be cases of, the first case in the master theorem. So the next case is when the ratio is some value less than 1. If the ratio is some value less than 1, if you get back to this this formula here, if the ratio is less than 1, the summation will be in theta of 1. The summation will be some constant value. So that constant value can be ignored the total time complexity in the second case is going to be O of n to the power of d. Okay, so what are some examples of this? These are 4 different examples of the second case. For each of them, so for example, for this one, if you calculate the, A is 3, B is 2, D is 2. What is the ratio? The ratio was A divided by B to the power of D. 3 multiplied by 2 to the power of 2. This is going to be 3/4. This is less than 1, right? So it falls in the second case. So the time complexity here will be theta of n power 2. For this case, again, if you calculate the ratio will be less than 1. So this one is going to be linear. This one is going to be linear. You see, in fact, all of these terms, like if the coefficient, the value of A is 1, and this is a term which is smaller than n, whatever is going to be actually the value of this one, this is going to be the result of the final, complexity of the value. So these are different cases of the different examples of the second case. And the last case. The last case is when the ratio is greater than 1. Okay, when the ratio is greater than 1, if we actually get back to here, let me just clean up a little bit to make it more readable. If the ratio is greater than 1, so the summation will be equal to the ratio to the power of k, right? Multiply by n to the power of d. So what is going to be the results for the last case? T of n will be equal to n to the power of d multiplied by r to the power of k. But I need to actually simplify this. What is r? I know that r is equal to a divided by b power d. If you take it to the power of k, what is the value of k? The value of k is going to be log of n. So r to the power of k will be equal to a to the power of log of n in base b divided by b to the power of d log of n in base b. Okay, so if I simplify this term, it will be equal to, let me write it in a more actually clean space. It will be b to the power of log of n to the power of d in base b. So you can simplify this as, because it is b, that you are taking it to the log of whatever in base b. The result is going to be n to the power of d. Okay, so this is again just discrete math. So this term will be equal to n to the power of d. And the numerator, let me use a different color. Numerator will be a to the log of n in base b. I can simplify it and write it as n to the log of a in base b. If you don't know this formula, this is coming from discrete math, so you can actually go back and review discrete math. I can simplify this formula and convert it to this. Okay, so the final result of r to the power of k will be equal to n to the power of log of a in base b divided by n to the power of d. If you multiply it to n to d, so in total t of n will be equal to n power d, n power log of a in base b divided by n power d. So this term will be simplified. T of n will be equal to n to the log of a in base b. Okay, so this is exactly showing the last case. That tells you that T of n will be in O or theta of n log of a in base b. Some of examples of this, all these relations will fall in the third case, where, for example, in this case, the value of a is 2, the value of b is 4, so a divided by b to the power of d, you know the value of d is 0, d will be 0, that's n to the power of 0 will be equal to 1. So the ratio will be 2 divided by 1, it will be 2 greater than 1. So this will actually end up to the third case. The time complexity will be equal to n to the power of 2 in base 4. So 2 in base 4, the log of 2 in base 4 will be equal to, half, or this is going to be equal to n to the power of 1 over 2. This is going to be equal to a square root. So the result of this relation will be in theta or O of a square root. Or for example, for this case, A is 8, B is 2, D is 2, and the ratio will be 8 divided by 2 to the power of 2 will be 2 greater than 1. So T of n will be n to the power of log of a, which is 8 in base 2. So this is going to be theta or O of n to the power of 3. Okay, so you can see more examples of more examples and more exercises in your textbook as well. Here is the summary of the full master theorem that we have discussed. It is actually just talking about, you can simplify the ratio. What was the ratio? The ratio was a divided by b to the power of d. And based on, comparing that ratio greater than 1, less than 1, or equal to 1, all of those cases can be actually also simplified in this form if you wanted to memorize it. Although I don't, recommend to memorize the formula. I just recommend you to learn how we got the formula, how we did the full actually proof, so you would never forget it. And this formula for the ratio of R is going to help you a lot in many other cases. Okay, so using the master theorem, you can actually solve many of these examples that I have written here, although some of them cannot be actually, master theorem cannot be applied. For example, these two cannot be solved using the master theorem. Yet you can solve problems like this using the substitution method, or using the recursion tree. Still, substitution method or the recursion tree are the the most general approaches to solve any recurrence relation. So I'm going to finish this lecture by just in fact solving a couple of more problems, which some of them can be solved using master theorem, some of them not. So if you have a relation like this, you can use the master theorem, right? It is easily will actually fall in the form of the master theorem. The value of A is 1, the value of B is 2, the value of D is 0. So if you apply what is going to be that ratio, A to the power of A divided by B to the power of D, this is going to be equal to 1, right? So I can actually simply conclude that this is going to be theta of log of n. The ratio was equal to 1, so it would be n to the power of d log of n. N to the power of d is going to be 1, the value of d is 0, and so the total is going to be log of n. But even if you don't want to apply the master theorem, you can simply just use the substitution or the recurrence tree. You can see that here the recurrence tree is not really looking like a tree because there is only the factor is going to be 1. T of n is equal to just 1 t of n divided by 2. You can actually just write it down. Still this is a tree, but it more looks like a linked list instead of the tree. So you can actually get the costs for each of these boxes, how many boxes you have, because the cost of each box is 1, how many boxes you are going to have. This is going to actually go down until log of n times, right? So it is very clear that the cost is going to be, log of n. It is very similar. If you think about the recursion relation here, this is very similar to binary search, right? In the binary search, each time you solve half of the problem, and the additional cost is constant. Another formula, you see that this is different than the previous one because this term has changed to n. Again, you can apply the master theorem, and you will see that if you actually apply the master theorem, the result of this formula, the ratio is going to be A is equal to 1, B is equal to 2, D is equal to 1. So the ratio is going to be 1 over 2. This is less than 1. What is going to be the final result? The final result will be O of n. Okay, this is going to actually fall in the second case of the master theorem. Again, you can, instead of directly using the master theorem, you can just go with the substitution method or using actually the tree. This is going to look like this, the summation of n divided by 2, n divided by 4, and go on. The result is going to be, you can in fact think of it in the reverse way. In this summation, you can think of it as these are going to be all, again, the powers of 2 until you reach to n. So the result is going to be 2n, or it's going to be actually O of n at the end. Okay, here I have another interesting example that in the previous cases you could apply master theorem. In this example, you cannot apply the master theorem, right? Because you can see that I have two terms to a smaller subproblem that the size of them are different. So it doesn't fall directly in the master theorem format that we had. We cannot directly apply the master theorem to this one. But what can we do to solve a problem like this? Still, I can apply and create the recursion tree, right? So if I create the recursion tree for this relation here, it will look like this, that T of n is going to be 1t of 2n divided by 3 plus another t of n divided by 3. Again, this one will be actually expanded to t of whatever is 2n divided by 3, you need to actually apply to 2 divided by 3. So it's going to be 4n divided by 9, right? And t of the size here is going to be 2n divided by 3. You need to divide it by 3 again. So this is going to be 2n divided by 9, right? You get where I got actually this 2n divided by 9. I'm using the same formula here. So I got 4n divided by 9 here and 2n divided by 9 for this part. I will apply the same relation for this one. So you know that t of n divided by 3 will be equal to t of 2n divided by 9 plus t of n divided by 9 plus that additional cost n divided by 3. So I'm going to actually use this formula for this one. So it's going to give me t of 2n divided by 9 and additional t of n divided by 9. Okay, so let me just clean up a little bit here. So far I have created, I developed the tree until the second level. You can continue actually developing the tree, but before I do that, I'm going to actually just, added that costs that for each of the boxes we are going to have. We are going to have this additional cost based on the size, right? So I have n, I have 2n divided by 3 here. I have, again, the size here is n divided by 3, so it's going to be additional cost here. The cost of this box is going to be 4n divided by 9, 2n divided by 9, 2n divided by 9, and n divided by 9. So if you look at the summation of the cost of each level, what you are going to get is the cost of the first level is n, the cost of the second level is n, the cost of the third level is 4n divided by 9, 2n divided by 9, 2n divided by 9, and n divided by 9. The summation of all of that is going to be n. Isn't it nice? Okay, for each level, I actually figure out that the cost of each of these levels is going to be 9. But still, I have to actually solve something. How big would be the tree? What is going to be actually the depth of the tree? Something about this tree that I should consider is that the tree is not going to be, like the previous trees which is going to be a full tree until the leaf level. In this case, some of the branches, like this one, is going to reach to T1 much faster than some other branches, like this one, that is going to take longer to reach to T1, right? Because here I am dividing n, keep dividing n by 3, so I will reach to 1 much faster than the cases that I would multiply n to 2 divided by 3. So it's going to actually reach to 1 slower. So this tree is going to be uneven. So the previous discussion that we had is not going to be, easily applied to this one. I cannot, I don't have a, a fixed depth level for all of the leaf nodes in the tree. So what can I do? A method that I can apply here is I can find an upper bound for the cost of the tree and a lower bound for that. So assume that I would stop the full tree at this level. The earliest step that you reach to the leaf node, if you stop all of the, developing the full tree at this level, it's just like you are ignoring some part of it which is growing on this part, right? So whatever is going to be this summation, the summation of the tree on top of this level, this is going to be a lower bound for T of n. Okay, so what I'm going to do is finding a lower bound, finding the cost for the lower bound, and later on finding, then in the next step, I'm going to actually find the cost of a tree that, assuming you are growing it on all these values until to actually the last level that you reach to T1. So this is going to give me an upper bound for T of n. So I'm going to find a lower bound and an upper bound for T of n. If both lower bound and upper bound for T of n are going to actually fall in the same, for example, theta notation, then the total time complexity of T of n are going to be the same as the upper bound and lower bound. But if they are different, at least I would have a, some analysis, right? I would have a lower bound, I would have an upper bound. But let's just first calculate the upper bound and the lower bound. And be careful, this, so you can actually see that instead of actually the lower bound, I can write using the omega, right? So I can actually say that what is theta in terms of the omega, and what is going to be the upper bound. So what is going to be T of n in terms of big O. So these are the two different actually questions that I need to solve. What is the upper bound? What is the lower bound? So in the case of, so this is going to be actually, the full tree. We are first interested to actually find the lower bound. Okay, if I'm going to find the lower bound, you see that the cost of all of these levels are n, which is actually make it simple. I just need to figure out how many levels I will go down to reach to this lower bound. You can see that the size of the problem will be divided by 3, keep dividing it by 3 until you reach to 1. So it's just like you n divided by 3 power k equal to 1. So n will be equal to 3 to the power of k. K will be log of n in base 3. Okay, and remember, we don't really care about the bases of the log, so it's just like the k is going to be log of n. So what is going to be, maybe the color yellow is not very nice to show, but so the lower bound for t will be n multiplied by log of n, which you actually need to put it in omega. Okay, so this is going to be a lower bound for, this is going to be a lower bound for t. What is going to be the upper bound? So for the case of the upper bound, we assume that you actually keep growing the tree even for these parts that which are not going to be in T of n, but assume that the tree is going to be fully developed until this level. So again, the cost of each level is n. How many levels you are going down? The number of levels that you are going down will be depending on changing the size here, right? So it is going to be 2n divided by 3, then it will be 4n divided by 3. Or if I actually wanted to simplify it, this is going to be n divided by 3 divided by 2 to the power of k, where k here is going to be the number of depths on the longer side. So if you simplify this one, so you can see that n will be 3 divided by 2 to the power of k. So k, the depth of the tree on the longer side, will be equal to log of n in base 3 divided by 2. Okay? Again, this is going to be log of n because we don't really care about the base as long as the base is greater than 1. Okay? So even for the upper bound, what we can actually get is O of n log n. Okay, so we solved the problem. In fact, the lower bound that we found for the problem and the upper bound, both of them are going to be the same. So I can say that I know the the exact growth ratio for T of n, which is going to be theta of n log n. So this is an example of having, you see that this problem cannot be solved using the master theorem, but still you can apply the the recursion tree and solve this problem easily. Another problem, I try to actually write down the full recursion tree for this case and solve the problem. If you find it actually difficult, we can discuss about it in class. I also actually have the final actual solution here if you wanted to have a look at it later. The result of this relation will be O of n. In fact, this one is a very nice one. Try to actually solve it, and if you had any question, we can discuss about it in class or during the office hours. Some other actually cases that the master theorem cannot be applied, T of n equal to 2T of n minus 1 plus 2. You can see that this is not a form of the master theorem. So you can simply just apply the substitution method for this one, or even the recursion tree. So if I use the substitution method, this is going to be, you can see that each time. So if I keep substituting this term to T of n minus 1 plus 1 plus 1. So this is going to be, if you simplify, this is going to be 2 to the power of 2T of n minus 2 plus 2 plus 1. And if you keep actually going, this is going to, in the second level of substitution, this is going to look like this. After a couple of steps, what you will see is that the size of the problem is decreasing by 1, and each time you are actually adding another term of 2, and all these terms will be actually added. So when you are going to stop, when you reach to T of 1. And how many steps? You can see that I am decreasing the size each time by 1, right? So what is going to be that multiplication here? That's going to be 2 to the power of n plus 2 to the power of n minus 1 plus 2 to the power of n minus 2. And this one will be actually replaced with 1. So this is going to be a summation of 2 to the power of I, where I started from 0 until n. Okay, so this is going to be 2 to the power of n plus 1, which is going to be 2 multiplied by 2 to the power of n. This is going to be an exponential function. So if you write a recursive relation, like a recursive formula like this, if you write a recursive algorithm that has this recurrence relation, this is going to be exponential. It just simply shows you that each time that you decrease the size by 1, and you are multiplying it by 2. And so that's why it's going to actually grow exponentially. How about, a relation like this? Is it going to be faster than the previous one? Of course, this is going to be slightly faster, because instead of 2 terms of t of n minus 1, you have 1 term of t of n minus 1 and the other one to be of t of n minus 2. But is it going to be, considerably faster than the previous algorithm? Does this relation reminds you of anything? If you think about it, you will see that this is exactly the recurrence relation for the Fibonacci algorithm. If you calculate the Fibonacci using a recursive algorithm, this is going to be the recurrence relation for that. And the cost of that is going to be still in O of 2 power n. To be more exact, is of course, that base can be actually smaller than 2. Although this is not still exact as theta, but this is a more, tighter upper bound. This is better than 2 to the power of n, but still this is an exponential function, and shows you that if you have a recursive formula with this recurrence relation, this is going to be really slow. Just like if you write the Fibonacci algorithm using a recursive relation without actually saving the cache, this is going to be very slow. Okay, I have a couple of more examples at the end of this slide that, of course, the length of this video have been, I think I took a long time discussing this video, but let me solve just one of these problems, and I have the solution for a couple of more problems here that you can just read them later, and if in case you had more questions, you actually come back to me during the office hours or in class. So how about solving a recursive relations like this? Again, you can see that this cannot be solved using the master theorem, right? I don't have the, that simple form of n divided by b for the sub-problem. So this cannot be solved using master theorem. But still, I can use the substitution method, or I can use the, recursion tree. Yet, you can see that these sub-problems that I have is, actually looks very complicated, because it is applying the square root to make the problem smaller, to actually decrease the size of the problem. So what can I do here is to use a kind of, simplifying the form of the problem, the size of the problem, and rewrite it in another actually function. The first thing that I am going to do is to assume that n is equal to 2 to the power of k. So if I rewrite n in the form of k, I can also actually say that, okay, the n square is going to be n to the power of half 1 over 2, right? So if I write it in terms of k, it would be 2 to the power of k divided by 2. Okay, if I wanted to write t of n instead of in terms of n, I can write it in terms of k, right? So it would look like this. Still, this form is not something simple to work on. You would actually say that you are not really making it simpler to work. You are right. I need one more step to simplify this function and make it easier to work on. What I can do here is, to apply some combination of the functions. So I know that based on this definition that I wrote here, I can actually say that, let me clean up this part. I can say that n is some function of k, right? Where this function is going to be 2 to the power k, okay? So I can say instead of t of k in this way, which this one is not a t of k, in fact it is going to be t of n, right? I am going to combine these two functions. I'm going to combine t and h and create a new function g of k, which is in fact would be something like actually t of h of k, something like this, okay? So instead of this, it's just like I'm going to rewrite the whole term in terms of g. So it's just like I'm changing the argument, right? I'm changing the argument and creating a completely new recurrence relation. So for g of k, if I actually converted this part will be converted to g of k divided by 2. And this part is a fixed term, so I can actually just copy it here. So now I have a new recurrence relation, which I know how to solve it using the master theorem. I just simplified it, right? I simplified it and create a new recursive relation. So I know that g of k will be theta or O of log of k. Be careful, I'm talking about k, not n. Okay, so I have solved this recurrence relation. But originally, I needed to solve t of n. I'm looking for t of n. So what would be t of n? I just needed to get back and use all of these, in fact, this function h of k, which is going to be 2 power k, and I'm going to actually just replace k and convert it back to n. So based on this, I can say that t of n will be theta of log of, instead of k, you have to write down k in terms of n, which is going to be log of n. So this is going to be log of n. So this is going to be the result, the solution for t of n. Okay, so you should be very careful when you are using this approach for solving the recurrence relations. If you are converting your function to another functions by combining the functions, you should be very careful when you are actually converting it back to the original term, which is going to be n.